Hello everyone, I am Pranjal Sahu, a senior R&D engineer at Kitware Carborough, and I will be presenting our work on reproducible workflow for visualization and analysis of osteoarthritis abnormality progression. This work has been done in collaboration with the Computer Science Department at the University of North Carolina at Chapel Hill. The open source software described in this presentation is named OAI Analysis 2 and is present at the GitHub link shown below. The software has been developed with a focus to analyze the osteoarthritis initiative dataset, which can be downloaded from the link shown below. Osteoarthritis is the most common form of arthritis, which most commonly affects joints in hands, knees, hips, and spine. To quantify osteoarthritis progression, cartilage thickness is computed, which is taken as an indicator for bone health and arthritis damage. The software performs analysis of the knee MRI images present in the OAI dataset taken from around 4,800 patients. The osteoarthritis initiative is a massive dataset of around 15 terabytes. To perform analysis of this entire dataset, there is a need for a large-scale distributed computing software, and this work presents an open source software developed to accelerate this analysis. The software comprises 5 stages, which is also shown in the figure here. First, registration of knee MRI images with the atlas images. Second, segmentation of cartilage bone from the MRI images. Third, mesh extraction from the segmented images. Fourth, thickness computation using the meshes. And finally, projection of this thickness to 2D atlas space for visualization. An end-to-end demo of the pipeline is shown in a Jupyter notebook named Full Demo. The users can simply open it in a Google Colab and run it step by step. Now, I'll be describing the various steps in this pipeline with the help of the Full Demo notebook. To register the knee MRI images with the atlas images, we utilize a recently published icon registration model, which is a multi-scale, multi-step neural network trained with an inverse consistency loss. The model uses ITK interface for image resampling. The users can check the output of the registration using the ITK's checkerboard filter, which overlays the registered image on top of the fixed image. For segmenting cartilage bone from knee MRI images, we use UNet convolutional neural network model, which outputs the probability maps for the tibial and femoral cartilages. Users can see the output of segmentation model with the help of Matplotlib as shown here. The segmentation masks are then deformed using the deformation field obtained from the registration algorithm. Mesh processing is then performed on these deformed probability masks. To extract mesh from these probability maps, we use the marching cubes algorithm. The obtained mesh then goes through certain additional steps such as smoothing and connected component analysis to filter out small regions. For these steps, we use the open source software VTK. The mesh is then splitted into inner and outer components using the K-means clustering algorithm. The splitted components are shown here. For 3D visualization, we use the ITK widgets. Cartilage thickness computation is then done with the help of the splitted meshes. For this, we use the nearest neighbor method for each point in the inner and outer splits. Again, the users can utilize the ITK widgets for visualizing this thickness map in 3D. Here are shown the thickness maps for the femoral and tibial cartilages. As can be seen, users can freely interact with this 3D mesh. For 2D visualization, the 3D thickness map first needs to be mapped to a 3D atlas mesh. For this, we use the nearest neighbor method. The mapped atlas mesh is then projected to 2D surface. For the femoral cartilage, we use a cylindrical surface, while for a tibial cartilage, we use the PCA algorithm for projection. The mapped thickness mesh in 2D is shown here. 2D visualization is helpful in easily understanding the progression of the osteoarthritis. The objective of this software is to be able to perform this analysis on this entire OI dataset, or to perform this analysis for a single patient very quickly. For this purpose, we utilize a Python parallel computing library called Dask. Dask creates a computation graph based on the function called graph. This graph is then used to orchestrate the computation so that independent steps can be performed in parallel. As shown here, the call graph of the computation is translated into this Dask computation graph. Steps which can be performed in parallel are shown adjacent. For example, registering the images and segmenting the images can be done in parallel. Similarly, thickness computation for the tibial cartilage and the femoral cartilage can be done in parallel. This is extremely helpful in accelerating this analysis, as analysis for one time step can be done in parallel with another time step. The users can also test this functionality with the help of Dask Computation notebook in the repository. To perform this analysis on the entire OI dataset, one can leverage cloud resources such as AWS. We have tested our pipeline on AWS instances with the help of Coiled. Coiled provides an easy to use interface to scale computation to multiple workers on demand. Shown here is how the Coiled interacts with the AWS account. In our testing, we made 4 GPU workers on AWS instances and performed this analysis for one patient for both left and right knees for 6 time steps. We could finish this computation within 4 minutes. The Dask computation graph for this parallel computation is also shown here. As can be seen, the computation for different time steps can be performed in parallel. Depending on the available budget, the users can spawn n number of workers in AWS instances and can perform this analysis on the entire OAI dataset. This is very helpful in performing population-based analysis also. We have also shared a sample Jupyter notebook that demonstrates this computation on a Coiled cluster. The notebook is named Dask Computation Coiled. To run this notebook, the users will have to create Coiled account and will have to perform certain additional steps. Users are welcome to reach out to me for any help regarding this. Thank you.